Hello. In this video, we will prove two important theorems about divisions. The proofs will be very challenging to come up with, but I'll do my best to explain them. If you're feeling up to the challenge, make sure to pause the video at each problem and try to solve. Now, we begin. The division algorithm or the Euclidean division is something you're taught at primary school. But can we actually prove it? Here is what the theorem states. For all integers a and b with b greater than 0, there exist unique integers q and r, such that a equals b times q plus r, where 0 is smaller than or equal to r, which is smaller than b. Our proof will be slightly complicated to make. We have to prove two things. First, that such integers q and r always exist no matter the value of a and b. And second, that these integers q and r are unique. Before everything, I need to mention that a and b are fixed integers, whereas q and r are integers that we can choose their value since we want to prove their existence. Let's start by proving the existence. To do it, we're going to use proof by cases. This basically involves splitting the original statement into many subsets or possibilities, then proving according to each one. First case, and the simplest one, is a equals 0. When 0 is divided by any number, it equals 0. So we can simply choose q equals 0 and r equals 0. And the theorem immediately follows because 0 equals b times 0 plus 0. Case 2. A is greater than 0. The next step for me is to split into subcases from this case according to the values of b. First subcase, b is greater than a. I can set q equals 0 and r equals a. Because the condition to set r is it being less than b, so it can equal a when b is clearly greater than a. Thus, a equals b times 0 plus a. It becomes a equals a, which is true, that's why q and r exist. Subcase 2, b is smaller than or equal to a. Now that's going to be a bit tricky. The theorem assumed that b is greater than 0, which means that a is greater than or equal to b, which is greater than 0. We multiply every side by -1, without forgetting to invert the sign. Minus a is smaller than or equal to minus b, which is smaller than 0. We can then add a to every side. 0 is smaller than or equal to a minus b, which is smaller than a. As you can see, a minus b is a positive integer less than a. But I can't tell if it is less than b or maybe greater or equal to it. The trick here is that if a minus b is not smaller than b, then I will set a minus b to another variable and repeat the same steps I previously did until it becomes less than b and greater or equal to 0. I will call the number of times I have to repeat the subtraction of b from a to reach that condition, k, which is a positive integer, of course. So, a minus k times b is the only positive integer smaller than b. This k integer exists because its possible minimum value, which is 1, respects the conditions set by the theorem and our subcase, and it can only take a single value because if a number is smaller than b and we subtract from it b, it becomes negative. If we add b instead, it becomes greater than b, of course. So k can only take one value, and its minimum possible value causes no problem, that's why it exists. b is greater than a minus b times k, which is greater than or equal to 0. And as it is actually the first subcase which we have previously proven, we know the theorem is true for a minus k times b. Thus it can be written as a minus k times b equals b times q plus r. If we move the kb term to the other side, then we factorize, and that's it. We have written a as the division algorithm suggested when it is greater than or equal to b. From these two subcases, we have proven the division algorithm to be true when a is greater than 0. Case 3. If a is smaller than 0, starting from case 2, I know that minus a equals b times q prime plus r prime, because a positive integer is the negative of a negative integer, and the division algorithm works for positive integers, as it had been previously proved. We multiply both sides by -1. Q can take any value, so we're fine with it being negative instead of b, which is greater than 0. R, however, must be between 0 and b, which is a problem since r prime, which is a positive number, is being negated. Let's add b minus b, which is 0, changing nothing, of course. We factorize the minus b. I want you to take attention to b minus r prime, because b is greater than r prime. I know their difference is positive and also smaller than b, which is the condition for r. If r prime equals 0, what I said now won't work. But it's fine because if that's the case, we can just replace it with no problems. If it's not, the b minus r prime becomes r and q prime minus 1 becomes q through abstraction, which follows the division algorithm. When we combine all the cases, we get that the integers q and r exist regardless of the values of a and b. We're making good progress. Now we have to prove that these integers q and r are unique. To do so, let's prove by contradiction. Assume for the sake of contradiction that q and r are not unique integers. This means I can express a with two different q and r variables, such that q and q prime are not equal. R and r prime are not equal, and they're both between 0 and b. Since b times q plus r and b times q prime plus r prime both express a, we can equal them. We move the r terms to one side and the remaining terms to the other. We factorize the b, which means that b divides r minus r prime, since the division results in q prime minus q, which is an integer. Next, let's see the restrictions for r minus r prime. When we add these two together, we add the smallest sides together and the greatest sides together to get r minus r prime is between minus b and b. As we previously said, r minus r prime is written as b times q prime minus q. Before I continue, I will quickly remind you that every number here is an integer. If q prime minus q was less than or equal to minus 1, r minus r prime would be less or equal to minus b, which doesn't respect the restriction. Alternatively, if q prime minus q was greater than or equal to 1, it would make r minus r prime greater or equal to b, breaking the restriction again. So q prime minus q must be 0, which makes r minus r prime 0 as well. From this, we reach that q equals q prime and r equals r prime, which contradicts our initial statement, proving by contradiction that q and r are indeed unique. And just like that, we have proven Euclid's division theorem. Bezout identity. Here is a theorem you may have been taught at undergraduate level in number theory. If a and b are positive integers, then there exist integers c and d such that the greatest common divisor of a and b is a times c plus b times d. A and b are fixed integers like before, while c and d are integers we can choose since we want to prove their existence. But there is a problem for me with this. I don't know how to choose the integers c and d, and proof by case will not help me to decide that. So instead, let's try to come up with a conjecture after replacing with numbers. After using some random numbers, I noticed that the integers c and d always happen to make the smallest strictly positive number with a and b to get their greatest common divisor. For instance, with 9 and 7, their greatest common divisor is 1, which is the smallest strictly positive number possible to make. For the remaining numbers, their GCD is the smallest strictly positive number because it's a difference between multiples. If you're not convinced, try to come up with numbers on your own and reach a smaller non-zero positive number than their greatest common divisor. You'll quickly realize that you can't. But of course, this is not a way to prove, but rather a way to conjecture on how c and d are chosen. So I can conjecture that the smallest strictly positive value for a times c plus b times d is the GCD of a and b. Thanks to our conjecture, we now have a base to work on and a good idea about how to choose d and c. Yet there is also the possibility that my conjecture was actually wrong. But if that's the case, then it suffices to make a new observation, create a new conjecture, and repeat until we reach the proof. Let's define x equals a times c plus b times d, such that c and d are always chosen to make x the smallest strictly positive number possible. To make the proof, we will first have to prove that x is a common divisor between a and b. To prove x is a common divisor of a and b, we prove x divides a, then we prove x divides b. To do it, we're going to use something we proved minutes ago, the Euclid's division theorem. That's the beauty of proofs. Everything you previously proved can become a lemma or a theorem, a useful statement that you're sure is true and you will use to prove even more. So thanks to the Euclid algorithm, I know that a can be written as x times q plus r. We replace x, we expand. We move the terms so that r remains on one side and the other terms with a. We factorize the a. I've written the remainder r as the form a times an integer plus b times an integer, but I know that x is the smallest of that form. Furthermore, according to Euclid division, r is smaller than x and greater or equal to 0. Because r is smaller than the smallest possible strictly positive number of the form it's written under, it can't be strictly positive, thus r must be 0, which means that x divides a, as it leaves no remainder with Euclid division. We can do the same steps for b. Just like that, we proved that x is a common divisor of a and b. Now let's prove it's the greatest one. We will suppose x prime is a common divisor of a and b. This means that a equals x prime times m and b equals x prime times n, such that n and m are positive integers. We will now replace with these in x equals a times c plus b times d. We will factorize x prime. Since x is positive and x prime, which is a common divisor, also has to be a positive integer, we conclude m times c plus n times d is also a positive integer. And when you multiply a positive integer by a positive integer, you're bound to get a result greater than or equal to its factors. So x is greater than or equal to x prime, which means that x is a common divisor greater than any other common divisor. This proves that x is the greatest common divisor of a and b. So the conjecture was correct, and just like that, we have successfully proven Bézout identity. So in conclusion, when we combine ways of proving, we can rigorously prove any statement. And these statements can turn out to be very useful for proving even more important things, so they become theorems or lemmas. And I really appreciate that in maths. It's the reason why I love it more than any other science, the fact that its base is extremely solid and everything is proved with maximum rigor. For math to work, we only need to embrace very few basic definitions called axioms as truth, such as x equals x or what is 0. And then logic comes from such basic statements to prove way more complex statements, to prove everything. Truly beautiful. Thank you for watching this video. It is from a series I'm currently working on called The Art of Math. The next video may be about solving advanced probability problems. I also wanted to say that I really appreciate your feedback on the previous video. You can leave a like to support me and check the other videos I've made. Take care.